Today's lesson is Lesson 3.2, Newton's second and third laws of motion. While students are entering the classroom, show this slide on screen. When the bell rings, click this slide to remind students that they have 5 minutes to complete the bell ringer. While students are doing the bell ringer, check their attendance and distribute the classwork sheets. At the end of the 5-minute period, discuss this bell ringer with the students. Lesson 3.2 Newton's second and third laws of motion. By the end of the period, with at least 80% mastery, students will be able to state Newton's second and third laws of motion, solve problems involving Newton's second law, third law of motion, and uniform circular motion. Newton's second law, or the law of acceleration. When a net force acts on an object, the object is accelerated by an amount directly proportional to the force applied and inversely proportional to the mass of the object. The greater the force being exerted on an object, the faster the object moves. The greater the mass of the object, the slower the object will move in relation to a lighter object with the same force applied. In the two pictures at the right, a big mass, the tennis ball, is harder to accelerate than a smaller mass, which is the table tennis ball. In equation form, this law is written as F net equals mass times acceleration, where F net is the total force or the net force or unbalanced force in Newton, or the symbol is N. M is the mass in kilograms, symbol kg, and A is the acceleration in meters per second squared. Thus, a 1 Newton force acting on a 1 kilogram mass will accelerate the object 1 meter per second squared. If you apply more force to an object, it accelerates at a higher rate. In this picture here, a force is applied to the object, causing it to accelerate. In other words, the speed increases. But if you apply more force to the same mass, more acceleration is achieved. That means the speed increases faster. Weight is a measure of the gravitational force that a massive object, such as a star or planet, puts on another mass. From the second law of motion, F net equals mass times acceleration, our F net in this case becomes the weight, mass is still mass, times the acceleration A becomes the acceleration of gravity. So, the equation is written in the form W equals m times g. An object's weight on planet Earth in newtons is equal to its mass in kilograms times negative 9.8 meters per second squared. Newton's third law of motion, or the law of action and reaction. For every action force, there is an equal and opposite reaction force. These two forces do not cancel each other because they are acting on different bodies. Examples of Newton's third law: the hammer and the nail. The hammer exerts a force on the nail to the right. The nail exerts an equal but opposite force on the hammer to the left. The baseball and the bat. The baseball forces the bat to the left, an action. The bat forces the ball to the right, the reaction. For the tire and the road, the action, tire pushes on road, and the reaction, the road pushes on tire. Here, the action, rocket pushes on gas, and the reaction is gas pushes on rocket. Now let's go to uniform circular motion. What is uniform circular motion? Uniform circular motion, or UCM, is a type of motion in a circle at constant speed, such as these pictures. Thus, the velocity v on object in UCM is not constant because the direction of v continues to change as the object moves around the circle, but the object's speed or the magnitude of v is constant. Note that the velocity vector v is always tangent to the circle. Acceleration in uniform circular motion. Since the velocity v in UCM is not constant, even if the speed is constant but the direction is changing, there must be an acceleration occurring. The acceleration in UCM is called centripetal acceleration A sub c because it always points toward the center of the circle. Centripetal means center seeking. This implies that the direction of AC always changes. Moreover, in UCM, the velocity v and centripetal acceleration AC are always perpendicular to each other. The formula for centripetal acceleration is A sub c equals v squared divided by r. And centripetal force is Fc equals m times A sub c equals mv squared divided by r, where m is the mass in kilograms, v is the linear velocity in meters per second, F sub c is the centripetal force in newtons, r is the radius of curvature m, A sub c is the centripetal acceleration in meters per second squared. Let's look at some of the examples of centripetal force. As a car makes a turn, the force of friction acting upon the turned wheels of the car provide the centripetal force required for circular motion. As a bucket of water is tied to a string and spun in a circle, the force of tension acting upon the bucket provides the centripetal force required for circular motion. As the moon orbits the earth, the force of gravity acting upon the moon provides the centripetal force required for circular motion. Applications of Newton's laws. So far, we have these 6 formulas. Number 1, F net equals mass times acceleration. Or from this formula, if you solve for m, the mass, this is F net over A. Or if you want to solve for A, this is F net over m. The weight W is m times g. The centripetal acceleration is A sub c equals v squared over r. Centripetal force Fc equals m times A sub c, which is mv squared over r, where F net is the net or unbalanced force in newtons, and m is the mass in kilograms, A is the acceleration in meters per second squared, W is the weight, newtons, and G is the acceleration due to gravity, negative 9.8 meters per second squared. A sub c is the centripetal acceleration in meters per second squared. V is the speed or velocity in meters per second. And F sub c is centripetal force in newtons. Solve the following problems. Always start by writing the formula, substitute, calculate the answer, then write the final unit. Number 1. A car has a mass of 1,000 kilograms. How much force will you apply in order to push it 0.05 meter per second squared. So we are asked to find the force. The formula is F net equals mass times acceleration. Substituting for mass, which is 1,000 kilograms, and acceleration, which is 0.05, we have 1,000 times 0.05 equals 50 newtons. Number 2. If a force of 20 newtons accelerates a body 2 meters per second squared, what is the mass of the body? So we are asked to find the mass. Using formula number 2, M equals F net over A. And substituting the values, force is 20 newtons and acceleration is 2. Therefore, the mass is 10 kilograms. Number 3, a force of 5,000 newtons is applied to a 1,200 kilogram car at rest. What is its acceleration? So using formula number 3, acceleration equals F net over M. Substituting, we get 5,000 newtons divided by 1,200 is equal to 4.17 meters per second squared. Number 4, a 60 kilogram athlete runs at a constant speed of 10 meters per second around a circle of radius 15 meters. Find the athlete's acceleration. So, using formula number 4, since this is moving around a circle, A sub C equals V squared over R. So, substituting the values, V squared is 10 squared divided by R, which is 15, and we get the answer of 6.67 meters per second squared. If his speed is doubled, is his acceleration half, unchanged, doubled, or quadrupled? So let us verify using the same formula, but this time the speed is doubled, so it is 20. So 20 squared divided by 15 equals 26.67 meters per second squared, and we see that the acceleration is quadrupled. Letter C. Find the centripetal force exerted on the athlete and where it is directed. So using the formula Fc equals MEC, the mass is 60 kilograms and the acceleration is 6.67 meters per second. Substituting these values, we have 60 times 6.67 equals 400.2 newtons, and this is directed inward. Apply the method described above to construct free body diagrams for the various situations described below. Letter A. A book is at rest on a tabletop. Diagram the forces acting on the book. So, let us sketch the table and the book. So, there are two forces acting on this book and on the table. So, one is the force exerted by the table on the book, and the other one is the force exerted by the book on the table. So, there are only two forces acting here. If there are no more questions, then let the students complete the classwork until the end of the period.